Hi everyone, I'm from Automata and today I'm going to tell you how we use TE coprocessors to enhance ZK-Rollup security. So we start with the one on TEs. A TE, or trusted execution environment, is a memory enclave within the hardware that's protected from outside interference. That means neither the operating system kernel or the hypervisor can tamper with the data and code that's inside the enclave, and we ensure this by encrypting the memory of the enclave and allowing only the enclave to decrypt it. There are a couple of vendors that provide TEs, such as Intel, AMD, ARM, AWS, and they are basically providing a hardware root of trust for our TEs. So you might ask, how do I know that machine that I'm interacting with is actually a TE? And this is where remote attestation comes into the picture. So remote attestation allows an enclave to prove its identity by generating this attestation document, and only a legitimate TE is able to produce a genuine attestation document. The specifics of each attestation documents vary based on the manufacturer, but they will usually contain these three elements: the enclave identity, which is a public key that is recognized by the TE manufacturer, and the private counterpart of this public key is embedded inside the TE such that only the TE can access it. Then we have the enclave measurements, such as the software running on the enclave, its configuration and firmware, and so on. And lastly, we have a digital signature that's produced using the enclave's private key to prove that, hey, these are actually my measurements and this is why. So at Automata, we use TEs to build coprocessors. Why we need coprocessors? Well, the EVM is a constrained environment for doing computations. We are limited by the block limit on how much computation we can do per block. We can't do floating point math. The contracts have a limited amount of storage and so on. And on the other hand, the off-chain computation is, of course, boundless. But the problem when we move computation off-chain is that we lose the trustlessness and decentralization properties of the blockchain. So coprocessors aim to solve that by both allowing the EVM to do sophisticated computation, while at the same time providing a way in which we can verify that this computation was indeed performed. And everyone's favorite coprocessor is the ZK coprocessor. The problem with ZK coprocessors is that they are very complex, and they still come with significant latencies, complex implementations, and computational overheads. On the other hand, the TE coprocessors may not rely on the sexiness of math, but they are cheap, fast, and very practical. We can pretty much do with TE anything that we can do with a regular computing system. We just lose a bit of performance when we encrypt and decrypt data, and also, like, if we have many context switches from the enclave, the secure enclave realm to the outside world. So one way we use this TE coprocessor is to implement multi-provers. In particular, we build a TE prover for ZK-Rollups. Again, we go back to zero-knowledge systems being very complex and relying on advanced math. There are many ZK experts that can audit the code, and also the developer tools are pretty new and haven't been battle tested. Yeah, so because of this, it's kind of unlikely that the multiple tens of lines of code of a ZK-Rollup doesn't contain any bug. It's a bit silly to think otherwise. So instead of having the ZK prover as being the single point of failure in the ZK rollup, we add an additional prover in the form of a TE prover. So now the TE prover will observe what happens on the L2 and will generate this proof of execution. And if the ZK proof produced by the ZK prover and the proof of execution produced by the TE prover agree on what the state transition is for the rollup, that means the state transition is correct and we can accept it. Okay, for the TE prover, we use Intel SGX. If you've heard of Intel SGX before, you probably heard that it's been broken many times, and truth be told, it's gonna probably be broken again. But it's really not as bad as it sounds. For one, the bar to break the Intel SGX is actually quite high, and there are also many ways in which we can mitigate exploits on the SGX. So because of this, we do trust the integrity provided by the Intel SGX, and we rely on this integrity to trust the proof of executions that are produced by the TE prover. Okay, the performance is also pretty good, and our implementation uses the Intel SGX RISC ZK, and it has a minimal computation footprint. Okay, the TE prover is open source. It uses the Sputnik VM as the EVM interpreter, and we have both an SGX and non-SGX implementation. And by comparing the two, we notice that the performance loss is actually less than 10%, which is pretty good. And in fact, using newer TE technologies, we might be able to reduce this performance loss even more. Currently, the TE prover runs on both the testnet and the mainnet, and so far the ZK prover and the TE prover have agreed on what the state transitions are. Okay, we are also implemented a TE prover for Linea, which is open source, and we have a TE prover for the R0 VM as well, but we are currently still cleaning up the code, and it's not yet open source for the RISC Zero one. So as I mentioned, the TE technologies rely on this attestation to prove that, hey, I'm actually a TE. So part of our implementation also involves verifying that the attestation document provided by the Intel SGX is correct. And we implemented this in Solidity. This code is also open source. And actually, this implementation is it's fully done inside in Solidity, and it's a bit expensive because part of verifying the Intel SGX attestation document involves verifying a bunch of SCP-256R1 signatures, and these don't have support in the EVM. So actually, we have another implementation that offloads the computation to the RISC Zero VM, and by doing that, we managed to reduce the cost by roughly 10 times. We're also working on open sourcing that soon. Okay, so lastly, I would like to say a couple of words about our AVS. So the AVS gives the TE prover crypto economic security. So if, let's say, currently the TE operator wants to doesn't want to provide the multi-prover service for the scroll rollup anymore, then it can disconnect the TE from the network, and that will be a problem. Like the TEs can ensure integrity, but they cannot ensure liveness. So in order to solve this, we basically add the crypto economic security of the AVS, and now if the operator wants to disconnect the TE, then it will be slashed. And the AVS also allows us to build these TE committees that I'm going to talk in the next slide. But before that, I want to add that by having this T environment that is backed by crypto economic security, we can have these like T rollups that are very low latency, because the T can compute verifications very fast. So we can use them for applications like games, for example, that don't support latency very well. Okay, so now to the T committee. So we don't want to use only Intel SGX as the T vendor, because that's a bit of a centralization. So we want to use multiple T technologies at the same time. And let's say for the scroll rollup, they can say, I want the T prover to run on both AWS, AMD, and Intel SGX. And only if these three agree, then we say, yes, this is the correct state transition. So this doesn't only help with the decentralization, but it also raises the bar for potential attackers even higher, because now an attacker would have to break all these T's at the same time in order to do an attack. Okay, so this is roughly the AVS architecture. We have the operators with different T technologies. Then we have the multi-prover AVS, which includes the attestation layer, the layer to which we the layer that we use to attest that each T is genuine. And then we have the AVS contracts that deal with the risk taking and rewards and committees and so on. And on the right, you can see this reproducible builds. So reproducible builds help with preventing supply chain attacks. Like let's say you have a binary. How do you ensure that the binary was produced from a specific source code? So reproducible builds is a way to deterministically compile the software such that then you can verify that that a binary is indeed compiled from the right source code. And we work on this as well, and we actually do these reproducible builds inside the TE, and the binary that we get from there, it has additional properties, security guarantees. So now these operators can run these builds that are reproducible and be more sure that what they are running is correct inside the yeah, sure.
I know it's the layer package. So once certain there is a latency or there is kind of like a network issue with the any operator, they got slashed. So in that with this kind of architecture, we will have kind of double slash. So you have this kind of economic model to secure for if a multi-prover like this box, just to secure the service or protocol you are providing, and you might have another like, or this will help. I'm just confused. I might be wrong about my assumption, but is this kind of like help with the slashing problem in EigenLayer, or we might have another slashing problem because I might get slash on EigenLayer while I'm live on.
Oh, so the slashing only happens on EigenLayer. Then we rely entirely.
Does it help with the slashing problem, because it's a problem in EigenLayer when.
No, we don't do it. As far as I know, we don't do anything special. So if it's a problem on EigenLayer, then problem. Okay, so this is the architecture. Then a bit about stats. We have like about 98,000 stakers staking to like 16 operators, a total of 6.7 billion USD dollars in as risk-take it. That means that all this risk-take it and these operators are actually helping the scroll rollup to be more secure. And once we have the next iteration of the AVS, that will include Lina as well, and we are hoping to onboard other rollups as well. Okay, if you would like to learn more, these are some useful links. And that's it.